Okay, hello everyone, one more time. We're gonna talk about the kernel wars, anti-cheat reversing, bring your own vulnerable drive exploitation attacks, and much more about the cheating. And yes, let me introduce myself. My name is Ravshan. I'm working at OneSec as a security researcher, and also previously, before the OneSec, I have worked with the V8 exploitation systems, V8 bugs, overall with Windows internals, and deconstructing highly obfuscated Android fintech applications. Also, recently I have joined to firmware research projects. I have done a couple of good projects. I have submitted good vulnerabilities. Unfortunately, the link's not answered yet. And I'm also passionate about building custom tooling for program analysis. And thanks for AI, it's done too quick. If you know how to do, it's not a problem right now. Okay, this is my github.io. It's my website, and I have the X account. Unfortunately, I'm not that active that expected, but I will fix this. Okay. Also, let's talk about the cheats. Oh, we have that. Okay. Probably, I think everyone loves the games, overall the PvP games, online games, but we hate one thing, the cheaters. I hate them because they ruin all the time the games. And as we know, I relate the gaming like camping. Go to mountains, do some camping, play the guitar, make barbecue, and the delicious marshmallow with hot chocolate. And at that moment, we see our enemies, our mosquitoes. We hate them also. And unfortunately, they are not alone. They are always with friends and cheaters, as I call them, also like this. They're always a group of people who want to cheat. And what we should do, we kind of do the spray them, and they will be last, but unfortunately they also still should leave. And we use like the mitigation systems like gnats. And actually it helps, not at all. And let's get into the big industry. Overall, the cheat systems are big industry, as we know. By data of Inconic, if I'm not mistaken, for 2025, at 2026, cheat economy total is $8.5 billion. It's a huge amount of money. And the anti-cheat market, as we know, they are different. Starting from the easy anti-cheat, which owned by Epic Games, till Battle Eye, is a $13.5 billion. It's all data. Also, we have average months, the banned players overall in the 50 major games is over 400K. Also, the gamers who face cheating is more than 80%. If you play the CS2, it's crazy amount of cheaters because they hate playing by the rules. And what about the anti-cheats? Anti-cheats are like something like the rootkit plus spyware because they have the both functionality. They also spy because they send a bunch of telemetrics to their servers, and nobody knows what they do with this telemetrics. They analyze or they teach for their ML-based some detection systems. But it's actually the final result, final product is an anti-cheat system. And we have anti-cheats from easy anti-cheat, as we know, as a user mode service plus kernel mode. It has both systems. And we know the Vanguard, who played the Valorant, knows about this. And we have also the WAC, which is I think the worst one because it's easily bypassed. Not easily, it's kind of not too difficult to bypass because it only works on user mode. Didn't have the kernel drivers. If they have the control. Today's presentation I'm planning to do as the reversing, but why we need the reversing? Try to understand the data types, try to understand the obfuscated systems. I do it before the talk, that's why I know how it works. Let's get into the internals, which is basically easier. And all files will be on my repository. It's in GitHub. I will publish after this conference. All files, it means from making the duplicate of anti-cheat. We try to build a fully anti-cheat system which works as like something like the easy anti-cheat or a battle eye is in the minimal systems. And we'll have the simple game. Let's get into game. We have the roadmap. I divided into 5 tiers. It's a user mode attacks, handle stripping, have not protected games could be attacked in user mode if they don't have the kernel driver anti-cheat system. And we also have the injection image load monitoring, it's a defense system. We also check out the both tactics, attack and defense. We have the unsigned driver and DSC. Bring your own vulnerable drive. We will try to exploit some game at the end of this talk. And DMA, direct memory access through the PCs. Also, we will cover somehow the hypervisor attacks overview. We're not get into dig this system. Okay. We have the game.exe. We have the simple game, as you can see. It just works, and it has some values like the score, 100. We try to change, we try to read this value with different techniques. And always the cheating, of course, the building the cheats overlay is the reading some sensitive values. Not always is a modifying. In the case of aimbots, if you try to build aimbots, you probably just read is enough because you should know where the location of the player is. Okay, how we read this? User mode memory reading works pretty easy. You don't need any credits. You should be on the same level as the process and on the same privileges. It works pretty easy. You open the process, you give the permission, which type of permission you want, process VM read or others, and you give the PID, read process memory, and as you can see in the example, we can easily read with memory address.exe. We just copied the score address because we didn't try to search where it's located. As you can see, I also have the SLR system, address randomization. We talk about this later. And yes, we have. And half cheats read the memory. We have different types of reading the memory. Whoever played with cheat engine knows how to find the cheats. The game's memory. You first search the value, exact value, and you change somehow. For example, if in the case of money, you spend money and exchange it, and it's of course we change it on the same address. That's why in the first result, for example, let's search the $1,000 in the game. It will give you the 1,000 results, but if you spend this money, somehow you have, after spending $853, and you search the same value, and it gives only one result, because only this result is actually the score address, if it's not the reference after some manipulation. And we have the second way of finding the game memories address of values is it's first statically assigned in the game, and after some operation, it of course be dynamically changed. We also have them in Windows the mitigations like SLR and different things, we use the pattern scanning. We know where statically the first initial value of address is, and after this we know where it could be differenced dynamically. And of course we can change it dynamically. And if you don't know cross process is the handle points at different process than yours. And it's a wiki moment we have. Okay, let's talk about the OB register callbacks handle stripping. It's a callback, it's not an actual function. The main thing that of callbacks is catch the process and terminate it. How? We have the handles, different handles, for example, open process, duplicate handle, or create handle. When we try to run this process, we catch with handles, and we try to terminate them with, for example, given this example. And in this case, we built the kernel driver. This kernel driver will be loaded into the kernel, and we have 3 different binaries. The first is game.exe. The second one is the function which works in userland, and the third one is in the kernel. And we tell them that you should protect this binary. For example, we are creating D1 defense type kernel. As you can see, we loaded our kernel driver, we started it, and as you can see, I turned off the signing. It means we can run the unsigned kernel drivers for the tasks, of course. And we tell the set protect PID.exe, we give the PID, and we say that you should protect this binary. And as you can see, we initially have this application. We loaded our driver, we set protect PID.exe, we give the PID, and we try to read this process memory. And unfortunately, it doesn't give anything because the handle actually understands that handle is not terminating. I mean, it just gives the empty value or trash value which the program does not understand what is. And from this, we get the wrong handle. If we turn off this security mitigation, we can read easily. As you can see, we stopped and we can easily read the same value. Okay, why handle stripping is not enough? Because we can directly inject the code as an example DLL injection we have. In the first example, we tried to catch the cross-process handles, but it's not protected from DLLs. If you have ever tried to play the Euro Truck Simulator, they also have the multiple player version, which is modded by Trackers MP. First, my adventure in DLL injection has begun from there. I try to understand DLL injection, how it works. They fully built a mode by DLL injection. It means they fully control the game, or partial. As you can see, as an example, how we can run, as we don't have key examples. Here we have. What's DLL injection? I think everybody knows what's DLL injection, but I will try to explain one more time. We first virtually allocate the game, allocate buffer. We write the cheat.dll, the process game, and create remote thread, which forces then the game to run this. And DLL main executes the cheat. It's in this example. And you see here the processes have to run this. And as you can see, it's fully injected. It's easily injected without any problems. If, of course, if binary doesn't have any mitigations. And we have, for the defense side, image monitoring. It's a bunch of, actually in the kernel, Windows, in the Windows internals API has a bunch of different syscalls. The syscalls program functions you can use to protect your game. As an example, I take the ps-set load image notifier routine as a kernel path that registers all callback, which are firing. Every time you connect, the DLL will run .exe. How it works? I took the two kernel callbacks. As mentioned, it's callbacks. They are not function. I took two different callbacks, which are ps-set load image notifier routine and ps-set create straight notifier routine. And every time you load the game the DLL into the game, it fires. It tells, is it image signature level 0? Or is it unsigned DLL, or alert or terminate check? Or is it equal to creator PID or to the target PID? No. Remote injection detected. And cheat DLL will not function at all. And we can see here as an example by the logs, which gives the alert remote threat injection detected. First of all, we loaded there. As you can see, the kernel kernel driver is the same, and we tell that you should secure this binary. We give the PID, and it secures this binary and gives the result. And how the thing is terminated? It's terminated by the Windows API ZW terminate process. It's going too well. Okay. Why image monitoring is not enough? What about if we try to inject some malicious code, malicious process through the signed legitimate driver? In this case, we have two different options. Let's see. We have the callbacks. Callbacks, they are actually the arrays which are on database. And of course, database we can modify. Any user with ring 0 can modify the data pages, but we cannot say this is the same as code pages because they are protected by hypervisor HVCI. And to turn off security mitigations of anti-cheats, we have cheater, first of all, needs ring 0. To open the ring 0, it has two options. Write own driver or bring your own vulnerable driver. Why write own driver fails? Because it's not unsigned and it's not legitimate driver. This is why it's blocked by DSA, we talk about later. And we have the bring your own vulnerable driver, which can be bypassed. If this have some good, I call backdoors, but actually they are vulnerabilities, uses IOCTL, which then accesses through kernel read-write primitive, 0 callback arrays. It will clear the callback arrays, and anti-cheat runs, running, but diff forever. You will not listen what's going on in the game. If you know about the hypervisor protect code integrity, it's actually the code integrity which is above the ring 0, which protects all, the pages of the Windows which should be secured. Okay, and the second page. Driver signature enforcement, how it works. It works pretty easy. As we know, driver should be signed by the Microsoft certification center. That's why Without this, any admin cannot load the CYC files, actually the kernel files. And the trust chain, how it works. Microsoft root of trust, or hardware vendor we have, or signed driver CYC. The first of all, how it works. You load the CYC driver file if it has the wallet signatures and wallet certificate from the Microsoft. It will go and you can run in the ring 0. If you don't have, it blocks immediately. And you can try yourself. You can just turn off all the Windows Defenders, all the antivirus systems. You try and it gives you the same result immediately. Even not. If you try even the wallet signed certificate, it's the most interesting part because it should go through the Windows Defender first. And bring your own vulnerable driver. I take as an example the Novis MSR input-output driver. Why? Because it has different, in the internet, the write-ups. You can read easily. You can find anything about this. We have also loaddrivers.io, which has a bunch of drivers which are vulnerable. You can try to yourself to hack the games. Okay, it has IOCTLs. IOCTLs are like the talking with the driver. It's let's imagine like TCP, client and server, but we talk with user from the user land to kernel land with driver. And it has 4 IOCTLs: read MSR register, write MSR register, which could be used LSR hook. The first one we can use it as a kernel pointer leak, and we can use the 2 of them. Read physical memory, write physical memory. Take note, it's a physical memory, not virtual. It's making some difference because with some manipulation, we should find the virtual memory also. Okay. How it can be loaded? In the case of C files, it can be loaded like this. In case of from terminal, you can use the CS load type kernel, driver, path, and start. It's easier than loading it in a C, but it depends on your situation. And we created here handle to talk with the driver. And read LSR, MSR, prove the primitive. Okay, why we need this type of way of finding proving the primitive? Overall, what's MSR? MSR LSR is the model specific register, which has the same address in the CPU register. It helps to find us the base address to then find other libraries address, base address to work through the different primitives. For example, if you have ever tried to write the exploits, you first find the libc's base address. Somehow, you should find the base address, and after this base address, you go through all the libraries, you find the other primitives. Okay, like writing, reading the memory. Okay. What gives us this thing? Reading star MSR, it gives us the load address, which we bypass the KSLR. Reading the MSR will give the KSLR, the base address, and after this base address, we can go through the function calls. We can load the virtual allocate memory. We can do whatever we want actually. And verify physical read primitive. We can verify by handling the easy, because always on the first 1,000 on the page 1,000 bytes actually read 14 bytes. Each 14 bytes we read, and we try to find the primitive. We should verify this is a physical address to further work with the virtual address. And we need a U process. Okay, let's explain here more detail. I have here the diagram. Okay. We have the system U process. System process, through the system U process, we find the CR3, which helps to us walk process list virtually. And this case helps to us to find the game.exe U process. And after that, in the same way, we find the CR3, which through the CR3, which handles all virtual addresses, we can translate them from physical to virtual address and read the game's memory. U process consists of offsets in default. As you can see, we have in the Windows 10 2020 H2, which is my tested OS. And we can find the system U process via physical scan. First of all, we can scan the physical RAM. No CR needed here. We look for a page signature. First of all, PID should be equal to 4, and a valid page align it with CRT. And then we search the system. As I said before, why we search the first 1,000 the bytes, because always when the system booted, all this U process data lives in the low physical RAM and never moves. That's why it's always stable. We can find with this primitive always the first CR3, I mean. And we can walk active process link to find the game.exe. How this works? We can use the PS initial system process, which we have exported, which we found by NTO. Always the first exposed DLL, and then we can go through the system U process as I told you about this. And we can go to the next U process each time, search, and when we hit the game PID, after hitting the game PID, we read the CR3. If we know the offsets of U process, we can also find in a wall grid in the Windows internals. We can read the directory table base, which has the game CR3, and through the game CR3, we can translate any game virtual memory, like this, yes. As you can see, we have the 4-level page table walk for this. The most one we need is the PT table. First, we get through the base CR3. Then we move the PDP table. After that, we go through the PD table, lower, and after the PD table, we find the PT table, which is an entry to physical. And by the offsets, as previously shown, we enter to the exact game locations memory, virtual memory, and how it actually works in the code. And after that, after statically reversing the binary, we know where it could be allocated, and we know the virtual address. We can read this page with map IO space. It's easily also from exposit DLL. And let's go through this one more time. We drop silent vulnerable driver to disk. We created and loaded our driver, which is DSA bypassed. We create the handle. Through the handle, we have the kernel read write primitive. We read the ls start to take control over key IC system call 64, And from this, we take the base address, enumerate kernel models. We find the anti-OSKey ordinal base address. And for which cases we can use the MSR LSR hook. For different cases, first of all, we can load the shellcode to the system. What it does, KI system call 64, it's actually triggered every time you trigger the syscall. It means we can just replace its like call handler with MSR LSR hook. It's easy. Or we can just token saved, which has the privilege escalation to ring 0, but in the case of anti-cheat, it's not needed because it can be detected by the Defender system, Windows Defender. To prevent this attack, we can use it's called the VDAC allow list. We just block the bad drivers. As you can see, how it can be policy written. A simplified policy, actually. What would stop this? It can be stopped by VDAC allow list, or we can also stop the hashing the vulnerable drivers and preventing them, checking by hashes. Or hardware attested EC, which hardest one. Okay. We also have here the DMA, the direct memory access. I'll probably be honest, I didn't try this approach, also the hypervisor approach, because they are too hard for just bypassing the anti-cheats, because I already bypassed why I need this. But if you have the more advanced systems, you probably can try this. What actually direct memory access? You access the memory through the PCE, through the hardware. It does the, for example, SSDs. It does the network, it's called adapters. Or you can access through the hypervisor attack. It's before before loading the OS, you load your code, you load your malicious code through the hypervisor attack, and you inject your cheat, which is the ring -1. It's even above the OS. And if, of course, it's not fails, if your code is successful, you can easily manipulate with anti-cheats. But anti-cheats are also not that stupid. They also check the PIC purse. That's why the successful attack is not always the case here. And what we have in defenses? We have some good defense here. Actually, the best defense could be probably VDAC allow list and driver signature enforcement, if we include also the hash there. We have the interesting kernel callbacks, which probably EC's anti-cheat systems work. And thank you.
Thank you so much, Ravshan. And I think we can take one quick question. We're a little bit out of schedule because of some technical issues in the beginning, but yeah, there you go.
Who is ASLR bypasser?
Can you repeat one more time?
ASLR bypasser.
ES, a lot bypasser?
Yeah.
Sorry, I don't understand.
ASLR bypasser. Who is?
Is there in the slides?
Okay, can we have the slides back really quick?
I can show.
Okay.
Here?
ASLR memory.
Bypasser. Bypasser.
Yeah.
Yes. You mean what's that?
Exploiting. Bypass ASLR.
You mean how I bypass the anti-cheat alarm system?
Yeah.
As I show, I fully bypass by bring your own driver. When you access with the kernel ring 0, you don't need the bypassing the each syscalls because they only works in user land. And as the thing, the driver works as the same as on the ring 0, they don't have any permissions to check another driver's the callbacks. In case of kernel callbacks, it's the same on the level. Another kernel driver doesn't have permission to check another kernel driver what it does, but it has permissions to do this in user land. That's why any alarm will not be triggered, and we can easily bypass probably all easy anti-cheat systems. Actually, this thing is not the new. It's actually was on the EGR's bypass. This was quite popular, and after that, it moved to anti-cheat systems. Okay, I hope I can explain.
Yep, feel free to bump to the lunchtime or after the closing speech. Once again, thank you so much.
Thank you.